webinar. I'm Mika, the host from AI Camp. So before we get started, just want to do a quick introduction on AI Camp. So we are a global online platform for developers, engineers, and data scientists to learn and practice AI technology with the mission of make AI available to all developers. AI Camp have grown to over 70,000 tech engineers in the group, have hosted over 300 local tech meetups, workshops, boot camps, large tech conferences, and live stream most of the tech talks globally. We have local study groups in the major cities in the US, a few cities in Europe, India, China, Australia. You can take a look at the website to see our upcoming tech talks, crash courses, workshops that we offer. So here are the upcoming online tech talks we have. So on Thursday, April 18, we will have deep learning jobs on Hadoop. And on Thursday, May 2nd, we will have open source end-to-end AutoML by Salesforce. On Wednesday, May 8th, we will have deep learning on mobile device at NVIDIA. And on Wednesday, May 15th, we will have Grow compiler and runtime by Facebook. And most importantly, starting on May 7th, every Tuesday and Thursday from 10 to 12 p.m. Pacific time, we will have our online workshop on deep learning for developers. So in this course, you will learn the fundamental of deep learning primarily through a series of hands-on exercises guided by the instructor. This course will balance learning theory, working on projects, and hearing from guest speakers in the field. So students who take this course will be able to identify and frame problems that can be solved by deep learning, choose the right techniques to the problem, understand key deep learning concepts and how deep learning model works, build deep neural nets for classifications of images as well as structural data using Keras framework, and describe reinforcement learning and implement reinforced learning to play games. So going back to our main topic today, I know there's lots of information to take away. So today we are excited to have Yifeng Lu from Google Brain. So Yifeng is a staff engineer and manager from Google Brain team, tech lead of Google first AutoML product, called AutoML Vision. So tech lead of AutoML application across multiple Google products. So today, Yifeng will dive into AutoML tech under the hood and introduce the overall of Google AutoML, how to apply AutoML to push the boundary of research, how to design and build an end-to-end AutoML product. So without further ado, let's welcome Yifeng to talk about AutoML by Google Brain.
Thank you, Mia.
No problem. I share my screen and then you can start to share your screen.
Sounds good.
Okay.
Okay, can you hear my screen?
Yes, we can see.
Okay. Hello, everyone. Good morning. Thank you for coming. I'm Yifeng Lu from Google Brain team. I'm basically tech lead the first Google AutoML product through cloud to launch it for all users, which is called AutoML Vision. And later on, we work on more verticals for AutoML. Like for example, I TLM the AutoML Tables product, which is AutoML for tabular data, and also AutoML Vision for the on-device solutions. Basically, we will try to train a more efficient model for the mobile devices. I will tell more about that later. And I'm very interested to make machine learning more scalable and democratize AI through the industry and real world. Yeah, let's get to the topic. The first question I want to share with you is that imagine what is the bottleneck of the broad application of machine learning in the real world right now. Like we already talked about AI first or AI is coming every day, but seems AI is not everywhere right now. So we're asking this question. To answer this question, let's take a look at what the machine learning solution looks like. Basically, it has three components. The first one is the ML expert, the human. And then we need to have some data. And then we need some computation. With these three components, we think that we can make a solution for machine learning. However, not all of them are very scalable. So let's take a look at them one by one. First, Is data the bottleneck? We don't think so. For example, because data is already very full, digitalization is happening in every business. So big data and cloud service are very affordable and very handy for even for very tiny startups. You just pay affordable money and you can use a lot of cloud services to manage your data and store it and compute it. And for most of the business, the current situation is excess of data is the opposite, which meaning that we cannot efficiently exploit the data we have to make a revenue. So that's why we think data is not the bottleneck. Uh, is the computation the bottleneck? We don't think so too. This is based on investigation from OpenAI last year, shows that the AI computation is doubled every 3.5 months since 2012. And this speed is really crazy, and it already beat the well-known the Moore's law, which is doubled every 18 months. So since 2012, the AI computation already increased 300,000 times. That is the plot in the right hand is show why this where this number comes from. The y-axis is actually after logged. So although it sees linearly, actually it's exponential. So you can see that in recent years the computation is exponentially increased every year, from the well-known AlexNet in 2012 to the AlphaZero in 2018. And this is because this increase is because a lot of like recent work on the AI accelerated hardwares, for example, like GPU and the TPU, and we believe that this trend will increase, will continue. So that's the reason we think that maybe the computation is also not a bottleneck for AI. So then we think that the bottleneck is actually the machine learning expertise. Machine learning expertise is a scarce resource globally, and the supply and the demand gap is huge based on different job hunting website like Indeed and LinkedIn shows that there's more and more machine learning engineer and data scientist requirement, but in short time, we cannot quickly train a lot of machine experts to fulfill the requirement, like the Yusha Benjo, which is a very famous machine learning expert, said that it takes years to train a machine learning PhD to be an expert to play with the machine learning. So if the bottleneck is the machine learning experts, let's review this formula and see how could we change it a little bit to make the machine learning more scalable, other than bottleneck by the human. So we want to adjust the formula a little bit. Firstly, we are thinking that could we materialize some of the best machine learning expertise into an algorithm and make it as automatic as possible, which we call this algorithm AutoML, and plus the same data. For those logical, which is very complicated, and for those domain human knowledge, which is very complicated and cannot be materialized as algorithm, we pay 100x more computation. Then it becomes a new formula for the machine learning solution, which is AutoML algorithm plus data and plus 100x computation. If we can do it this way, then it changes the game a little bit. Compared to ML, which is our current situation, the number of machine learning applications actually capped by the number of machine learning experts globally, we can change it to the AutoML context, which is number of machine learning application could scale with number of computations. That means if we can build more computation, more hardwares, then we can solve more machine learning applications, which seems more promising than in short time we train a lot of machine learning expertise. So with AutoML, we want to scale the machine learning with computations. That's a motivation why we propose AutoML. So someone may ask, is it a zero-sum game or win-win game? For example, whether AutoML will replace the data scientists and make them lose a job or something else, or it's a win for both of them. We think AutoML is assistant. It's not proposed to replace the data scientists. Instead, it's try to scale the machine learning expert scope. Uh, by materializing the expertise of machine learning expert, we can extend the human's impact. And by automating the workflow, we can improve the productivity of the human. So in both ways, we actually make this cake bigger instead of do a zero-sum game. For example, currently one data scientist can only focus on 1 to 2 modeling concurrently, but later maybe with AutoML, one data scientist could deal with 100 modeling tasks concurrently. That make more machine learning model to deliver to the industry, and more machine learning application meaning more efficiency improved in the industry. So it's a win-win game for both machine learning expertise and the industry. Okay, then come to the second question. What is AutoML? AutoML, short by the automated machine learning, actually provide automated method and the process, try to have two goals. The first goal, to accelerate machine learning research. The second goal is to make machine learning available for everyone. I will share with some ideas with these two goals. Firstly, let's take a look at the machine learning workflow in general. Machine learning workflow come with the first stage is like what I call it hardwired architecture design. Basically, what we do about feature engineering or architecture design, for example, how to design the ConvNet to make a vision task is kind of drop in this bucket. Basically, we need to define or design how we deal with those features with some determined decisions. Like for this feature, we do log transform. For that feature, we do embedding with 100 dimension size, something all like this. Why I call it hardwired, because later we will train the weight or optimize the weights inside this architecture. At that time, the architecture itself is kind of fixed, because we cannot change the log transform anymore. For any example, we will do log transform if we decided to. Only thing we can change is the hyperparameter, the parameter or weights inside each inside the architecture, which is optimized commonly by the back propagation, or there are other ways to optimize that. So the first stage is very critical in many machine learning domains. Although the second stage is also very important, our research actually kick off from try to see if AutoML can design a better hardware architectures. And later and later, we may focus on more stage of the machine learning workflow. For example, after we have optimize the weights and parameter, we will do model selection and ensemble to have more better generalization of the model, and we will do model compression and export to make it serving friendly and improve the serving performance. But our team actually kick off to solve the most core part of this workflow, which is how to design a better hardwired architecture by AutoML. So the challenging here is that the hardwire architecture design is not a differentiable problem. So we cannot use gradient descent to optimize in general. But recently, there might be some other research could do that way, which is some promising research direction. But in general, it's not differentiable. For example, whether we want to use log transform or we don't use log transform, this is not differentiable to the target. And also, sometimes we're facing a multi-objective optimization. For example, the architecture we design need to fulfill both high accuracy and very efficient, meaning the inference latency are good or the model size are small. Some of those constraints need to be considered together, which make it even harder for the design. So this problem is a little bit like the species evolution in the real world. Our idea is like this way. We have two players here. One we call the controller, and the second one is called the trainer. The controller is like a very smart guy. He generally propose different DNA for this species, and the DNA will be kind of like the protein synthesis. It will, but we call it model synthesis, which meaning the DNA itself is kind of a sequence of information. But based on this information, can we build a model or synthesize a model? Like based on the human DNA, we can synthesize a human, materialize the DNA into an object. And here the object is model. And we validate this model to say how good it is in the environment. The validation could be in very different ways based on the task. Sometimes we validate it as by using validation accuracy to say, hey, how accurate it is. And sometimes we will consider more things besides the accuracy. We may consider, say, how efficient this model is based on, for example, the latency on a specific device, and combine the accuracy and the latency together as a feedback. After the validation and the feedback, somehow we will design an algorithm to say whether this DNA is good or bad, or how good it is, how bad it is. So this DNA and the feedback pair will be a feedback to the controller. And the controller has another algorithm, which is called DNA optimization, that it will, based on this feedback, try to figure out an optimization route that could optimize himself in order to next time, if he want to make a proposal again or make a design again, he will make a better design. So if you can see this loop, if we continue to run this loop automatically, the controller will propose better and better design, and the trainer will, based on this new design, try to give them more feedback to say, hey, this is even better, this is worse. And the controller will be smarter and smarter and design better and better architectures. So this is basically the main idea of the AutoML research for architecture optimizations. By using this idea, we actually try to firstly design a better architecture for ImageNet. The green box is how human, based on the domain knowledge, the top human experts globally try to manually design an architecture to get a better ImageNet benchmark. And later on, when AutoML kick off, we actually could do better on top of the human domain knowledges. We automatically design or even better architectures, shows on the red box. And it is still the state-of-art architecture for ImageNet. And we go beyond, say, we because in this task we only target the accuracy, but later we want to say if we can build both accurate and efficient network by using AutoML. That's why we come up with research work our team called MNASTAT. Uh, it actually designed a state-of-art mobile vision model compared to previous state-of-art, which is well known as MobileNet V2, which is also from Google. Um, from the right chart, you can see that this is actually two-dimension chart. We consider both accuracy, which is y-axis, and the latency, which is the x-axis. And the upper left corner is the better one. So based on the black dot of MobileNet V2, the MNASTAT which could do significantly better to trade off the accuracy and the latency. So I can give you an example with the same accuracy as MobileNet V2. The MNASNet, which MNASNet can do almost 2x faster at inference time. That's a significant improvement on efficiency. So we apply this AutoML research idea and framework to assist the Waymo researchers. Because in Waymo's task, they need to consider both the state-of-art accuracy to push the boundary of their car's vision system's accuracy, as well as consider the performance or latency, because it's not a cloud cluster computing. It's a like local on-device computing. So they have to do it very fast to have a very agile feedback for the car to control. So actually, by using this idea, we improve Waymo's core vision system like the LiDAR segmentation and traffic light detection and the localization systems, and reduce the error rate by 10% on top of their existing very excellent accuracy error rate. And we already deployed the auto-designed AutoML models on their fleet. So the AutoML research idea has some limitations. Firstly, the customized DNA to model synthesis and feedback is a blockers for a lot of later on data scientists and machine learning engineers, because it requires a lot of domain knowledge to design the customized design, and it's very tricky. And we already see that it's very as critical as the controller algorithm itself. So if you design a very bad synthesis or feedback, even you use a very smart controller algorithm, for example, reinforcement learning or evolution, it may still fail to deliver a good result. And we haven't seen a general design across different various tasks that could workable. So for each task, we have to use a strong expertise to design these two components, which make it less scalable. Also, the DNA optimization algorithm or the controller algorithm is very low efficiency. It requires a massive computation to optimize. That means for the trainer part, it only can affordable to run on small tasks. For example, we in most cases we use CIFAR10 as a trainer job instead of the ImageNet, which is much bigger. And we have to, if the targeted task is a huge task like the ImageNet, we have to scale it down for the end-to-end search, the architecture search, and then design a very tricky, customized solution to how to scale up the architecture we find in the small task up to for the bigger task, because everyone knows that if we have more data, it's affordable to make the neural architecture deeper and wider to to make it have higher accuracy. So this part is still very tricky. Then we see that the automated research only solve half the problems we want to solve. We actually want to extend machine learning in two dimensions. One is the research boundaries we want to push. The other dimension is, can we use AutoML to solve more real-world problems? Seems AutoML research only solve half of them, and how could we scale machine learning to solve enormous real-world problems and make AI available for everyone? Then it's come to the second meaning of AutoML as an AI product. This is our idea. We want to have a product, AI product that with a couple clicks, everyone could build a high quality AI models to solve customized problem with AutoML. Here, AutoML is more about scalability and with very good quality and very strong, very excellent scalability to extend machine learning. So our idea is we want to build on top of our existing research and build a user-friendly and scalable and affordable AI product to solve massive machine application in the real world. It should meet this four criteria to be a AutoML product. Firstly, it should be end-to-end automatic modeling, meaning that it's basically a data in, model out pipeline. You just feed in your raw data and kick off the button, and automatically the model will be out for serving. And it requires zero human intervene for the pipeline and no customized setting cross tasks. And we don't, for this product, we don't expect it has the top one quality or state-of-the-art quality. We just want it to have competitive quality compared to machine learning expertise. For example, we imagine that it could rank among the top 20% of machine learning experts. But the strength is that it can automatically scale to 80% of the problems in domain. If we can do it this way, I think it could enormously scale the machine learning in real world problems. The third requirement is the budget flexibility, because we already see that for the big company, big business or small startups, their budget or their requirement are different. And we want the solution could be scaled on this budget plan. For example, if you only want to pay tens of dollars or $100, we can give you an affordable solution, although the quality is not the top one, but it's still very good. And if you are a big business, if you want to pay $100,000 or millions of dollars, we can give you the state-of-the-art result. So the user experience of the AutoML product should be like this. Firstly, you prepare your data set and labels. And then you set up your budget to say how much money I want to pay for this training. And then click the button. Then the whole pipeline automatically kick it off. And you can use the monitor window to monitor all the progress and the metrics of this training. And after the training will automatically done, and you can check out the final metrics of this model. If you are satisfied with that, you can during the UX you can do your batch inference or online serving directly and seamlessly. So let's zoom in the AutoML part of this product. Actually, the backend API, the high-level backend API look like this. There are only two input of AutoML. One is the data set itself, like where's the data and where's those metadata. For example, if you have a tabular data, then you have a lot of columns, and and you can update this CSV files and also describe, say, hey, the column B is a categorical feature, the column C is a numerical feature, something like that. Very simple metadata. You don't need to do very fancy feature engineering. No need to know what a feature engineer is. And the second input is the computations. Um, you need to tell the system that how much resources or budget you want to pay. Say, I want to pay $100 or something, and the system will figure out the coding computation you could allow to use. And then the whole pipeline just automatically run and return the model already ready for prediction or serving. If we do in this API, what we actually need to design and to do is that we need to automate every component of machine learning workflow. For example, we need to automate transfer learning if we decide to use transfer learning for this product. Or if we cannot use transfer learning, for example, currently for the AutoML tabular data, it's really hard to apply transfer learning. So we will do automated feature engineering, automated architecture design, and automated hyperparameter tuning, and automated model selection and ensemble, and automated model compression and export. If we can automate every component and we put them together as an automated pipeline, then the whole API is automated. I can give you a little some examples I'm currently working on. This is the product we just launched at the Google Cloud Next 2 days before through cloud. And the solution, we call it Ottoman Tables. Basically, we want to build an autonomous solution for tabular data. Imagine you have a spreadsheet or Excel, and most of the columns are features, and there's one column which is your interest, and the sum of these columns entry are empty, and you want to predict it or fill it up. Then you can just upload the spreadsheet, and the product will automatically model on top of that and fill those empty entries for you. So this product actually we are not just focused on the automation or productivity. We also want to make sure that it has the state-of-art quality across the market. We actually benchmark this product across multiple Kaggle competitions with other similar product from other vendors. And you can see the blue bar is the product. Actually, could do better than all the product in the market. And in most of the tasks, it can even reach the top 10% of Kaggle players level, which means it do better than 90% of Kaggle players in the world in this competition. And we want to make sure that it has affordable pricing. For example, the current pricing in cloud is like very affordable. And just yesterday, we used this algorithm as a first Kaggle bot to join an online competition with some in Kaggle Days San Francisco hackathon, and compete in 8 hours with top Kaggle player, and there are some grandmaster and master players there. And you can tell that we finally, in the private leaderboard, we get the second place. And the whole story is like this. At the beginning of the competition, we get the data as other player, the same time as the other player get, and we fit into our pipeline, and we just wait. And other player start to manual feature engineering, design the analysis, the feature relationship with target, do all the machine learning workflow. And then after the pipeline done, we submit the result, what we have. And we get the second place without any customization. So this is very promising because if we can solve this problem automatically, we in high chance we can do the same level in any tabular data computations. Another example is AutoML Vision, which is another product try to use end-to-end AutoML algorithm to solve the image classification problems. Here, the design is a little bit different because for vision task, we can leverage a lot from transfer learning. So what we did is that we firstly use AutoML research to discover the state-of-art hardwired architecture, which we call it NASNet. And we train it on ImageNet to get the weight, and then we transfer this weight and the architecture on the new task. And in order to fulfill the scalability, we need to generalize the pre-processing pipeline. For example, if you work on CV, you know that if you are working on ImageNet, you only need to think about how to deal with this RGB channel, which is the 3 channels. But in real world, there could be task of arbitrary channels. There could be 1 channel, which is grayscale images. There could be 7 channels, which could be some, LiDAR or sensor signals, which combine together as a fake image. This could happen in the self-driven car industry. They have a bunch of LiDAR and signals and then combine them into an image and use this fake image to do some tasks. So we have to deal with that. And we also later we try to leverage the Google level data for the pre-trained weights, and then we fine-tune all the weights on the new task, and we only research a very narrow range of the learning rate to make it to make the hyperparameter tuning adapt to the new task, and we use cosine learning decay to avoid more to reduce the number of hyperparameters, and we also do a model selection based on the continuous eval with low frequency, avoid to overfitting, and we do auto early stopping to save the budget. For example, if we see that this model already converged, we need to automatically stop it because even the total training step is not a knob for customer, because there are some customers even don't know how to set the total training steps, like how many epochs he should train if he don't have sufficient machine learning background. So we decided for them. What we do is basically we based on the task size to have a heuristic total training steps, and then we use auto early stopping to detect that if it already close to overfitting, we just stop the job to save some money for the user. Later on, I even extend this AutoML Vision for the more broad context of a machine learning application, which is the edge or the on-device context. The edge context could be very different from the cloud version, because you have to run the model in your phone or on the small devices, which meaning it has very limited CPU or computation and limited RAM, and commonly it need to power by battery, and you need to be very efficient to save a lot of batteries. So what we do to deliver this product is that we also leverage from the AutoML research, which is the MNASNet we talked before, to guarantee that we have a state-of-art quality and a very excellent latency and efficiency for mobile devices. And then we apply the TPU training to speed up the whole training procedures, which means we can even finish a 1 million image data set to converge in 24 hours. Someone may ask, like, how Is it very expensive or not? No. For all the AutoML product, we need to make sure it's very affordable. So we control it in $100 level for each task. It based on how big it is, and the price may vary, but around this level. And we make sure that after this pipeline or the output of this pipeline is already production ready, meaning it already support Keyflight, MLKit for in Google or Core ML for Apple. So the overall, the past 2 years or 3 years, what myself and my team are working on basically on part of this overall AutoML toolkits in Google. We focus on the AutoML Vision and the AutoML Tables. And personally, I participated in some of the work in AutoML languages, and there are other teams working on the video and translation to build the overall portfolio for AutoML for different domain of machine learning domains. So what's next? There's still more machine learning verticals haven't been solved by AutoML. For example, there are time series problems, there are forecasting problems, and recommendation. This could be our next interest, because if we want to use AutoML to make a machine learning scalable, we should cover all the domains. That's why we are motivated to solve more verticals and make machine learning scalable. And also, like I mentioned before, the architecture optimization algorithm or the controller algorithm is still very low efficient. So we are doing a lot of research, try to make it 10x, even 1000x more efficient. Then we maybe at that day, we can afford to do the end-to-end search directly on the customer task or the real world task. So the takeaway of today's talk is that AutoML scales the machine learning with innovative algorithm, automated pipeline, and sufficient computations. It has two goals. One is to push the boundary of research and accelerate them. And the second goal is to make AutoML as an AI product to scale on the real world problems and make AI available for everyone. Thank you, everyone.
Okay, thank you, Yifeng, for the great